Hello everyone, Professor Dustin here, and this video is going to be about forces and oscillatory motion. So one of the first things we're going to learn about in Physics 2 is oscillatory motion, which is a specific application of the things we learned in Physics 1. Specifically, we're going to take springs, which create oscillatory motion by bouncing back and forth, and study them in more detail using the mathematics and really calculus that we sort of did in Physics 1, just a little bit more carefully, specifically Newton's laws. So first, before going into any of the physics, let's just talk a little bit about the mathematics of oscillations and what the sort of plots of oscillations look like, and specifically what I'm talking about are sine and cosine curves, right? So let me get a cosine curve up here first. Okay, so there's a relatively nice cosine curve. All sines and cosines and other trig functions have two basic parameters which are going to affect how we study them. The first one is the amplitude. The amplitude is the distance between the equilibrium position and the maximum displacement. So in that case, that's here. Notice that we talk about the amplitude, it's from the equilibrium position, not from the absolute minimum. So really the object moves between minus a and plus a, so sort of a total distance of 2a. But when you talk about the amplitude, we're just talking about that part. And that'll be obvious why that is in a moment. They also have a parameter called the period, and the period of a trig function like this is the time it takes for the function to return to the same position again. So in this case, it's easier to draw on the cosine function as being the distance from right here to right here, from the peak to peak. Typically, we call that the period t, labeled t sort of conventionally. Capital P is sometimes used too. I've drawn it here peak to peak, but of course, the period is the same over the entire trig function. So if this would continue forever, and we could pick like trough to trough, that would also be the period. Or we could just talk about when it returns to the equilibrium position if I drew more of it from the 0 to the 0. Any of that is always going to be the period. Okay, cool. So now that we've drawn a good cosine function, how do we write this in an equation instead of just a picture? That's pretty easy. We call this x of t, and I'm using x because I'm considering this to be the displacement in the x direction of an object, let's say, which will be more clear when I actually do the spring. But it's going to be a position as a function of time, and it's going to be the amplitude of the motion times the cosine of omega times t. So now I'm labeling the sort of y-axis to be the time axis, but that's going to be that as time goes on, this thing is going to be bouncing back and forth. So the amplitude is right there. That's why we actually picked the amplitude to be equilibrium to the maximum position, because that's how you get that part of the function. And it'd be kind of awkward to write like a over 2 if you wanted to talk about that distance, because what goes in front of the trig function is the maximum distance away from the equilibrium, right? If the a wasn't there, the amplitude would be 1, because the cosine goes from -1 to 1, right? And here, that's the argument of the trig function. Normally we think of that as theta, but if you're talking about something which is changing over time, it clearly has to be a function of t. And as it goes, as time advances, the cosine function wants to go from its 0 to its maximum value to its 0 to its minimum value to 0, and then over and over and over forever. So that's the time value here. Here, this is called the frequency. It's omega, so it's actually angular frequency, right? And that's in there just to describe what's going on with the time there. So notice that like in the function there's an omega, but in the plot there's a period. And the period is a much more intuitive thing, like that's how long it takes for it to return to the same position. There's a formula that relates angular frequency and period, which you saw in the first video. It's very simple. It's just omega is 2 pi divided by the time, the period t. And of course you can see that if you put that into here, meaning you put it into there, when the time equals capital T equals the period, you get a cancellation between that t and that t. You get a 2 pi there, and that's when you get a cosine of 2 pi, and that's the maximum and the minimum value of the cosine is at 0, pi, 2 pi, and so on. We can go into more detail about that if you want, but you can also consider this just to be a definition of what this function is, and then what the angular frequency is that you put in, and how that's related to the period of the plot. There's one other thing we want to do, which is we want to talk about what if, so you can do a cosine, you can do a sine too, but you can do things in between, right? Like what if when I started my clock, I didn't quite hit t equals 0, right? Let's say that I got like, I just missed a little bit so that when I started my time, I started at like right here and not quite right there. So let me get a quick plot of that. right? So you can see what happened. I didn't quite hit the timer in the right place. I was a little bit late. This isn't going to work to describe this wave anymore because at t equals 0, you don't get a cosine of 0, which will be 1. You get a cosine of something not quite 0, right? So cosine of something that is like a small positive angle, right? So clearly like this doesn't quite work when you want to do this. It's also not a sine function because the sine has a 0 which starts there. Actually, sorry, it starts there and does this. So we have another way of writing an equation, that a wave that looks like that, and this is, it's very, very similar. It's an amplitude times the cosine of omega t, and then we have this additional factor plus phi. So that phi is just a phase shift of the wave. It says, actually, when t equals 0, we don't quite have 0 in here. We have a small positive angle, which is right here. Right, that little distance right there is that small positive angle. Because I didn't quite hit the time in the right place. Actually, the 0 of the cosine is actually a little bit behind the 0 of the time. But if I put in 0 right there, t equals 0, I get a small angle, and so that's what my cosine is. This is usually not a huge problem for us to deal with. We just have to know that that's in these trig functions when we want to plot them. Okay, cool. So that's a quick introduction to those waves. Now let's move on to actually doing a little bit of physics. Okay, so I've got a nice picture of a block and a spring here. The spring has a constant k. The block has a mass m. I'm going to pick the equilibrium position of the spring to be right in the middle of the block and pick that to be the coordinate x equals 0. So what I want to do is, okay, so I know that if I pull the spring this way, the block this way, and let go, the spring is going to pull it backwards, and then it's going to keep going, but at some point, the spring force is going to respond, push it back, and push it back, and push it back, and it's going to oscillate back and forth, hopefully with an amplitude A, with some frequency, and all these numbers. We haven't proven that yet, but that's what we're looking to do. The only way I have really of analyzing the system is using Newton's second law, which we did last semester. We are now prepared to analyze this thing, so let's go for it. Just like any good Newton's second law problem, let's get a free body diagram going on. So it's going to be just a point mass, no problem. That's going to be the block. Not worried about what I don't need to do a free body diagram for the spring, because when I write this thing, I'm talking about the motion of the block. So this is the free body diagram of the block. The block has a mass m, so I should write force due to gravity. And then I should write a normal force. But I'm just going to mention that I'm not going to consider anything in either of those two in the y direction because those two are balanced. It's on a flat surface, it's just bouncing back and forth. There's no action going on in the y direction, so I actually don't worry about those two forces. Now I'm going to worry about the x direction. Let's get a direction for the x direction. So I have x naught is 0, so that's the equilibrium position, that's 0. I'm going to do positive x to be that way, so let's just be super careful about that. But if I put the spring force onto my free body diagram, if I pull it this way and let it go, the spring force is going that way. So this is going to be for the positive x displacement. This is what the free body diagram is going to look like. Now, I have to be careful. This is like if I pull it over on this side. But if I push it over here, what happens? I get a different free body diagram. Let's do it a different color. I get the same vertical direction, Fn, Fg, but now the spring force has to go the other way. Because if the block goes this way, the spring force responds by going that way. So that's a negative x displacement with a positive force on this side, so that's over here. Over here we have a positive x displacement and a negative spring force. So we're going to have to deal with that pretty carefully. But let's move on. We have a free body diagram which looks like either one of those two on either side of the equilibrium position. So let's try to apply Newton's second law. Remember Newton's second law, sum of the forces. I'm only going to do the x direction is equal to m times a, only in the x direction. I want to sum up all the forces, so I have a spring force. Remember the spring force is kx. And what I'm going to declare right now, and then show you why it's true, is that if I put a negative sign here, it's going to take care of both of these two situations. So let's just quickly check that. If x is positive, you're over here. So for positive x, that negative sign says I get this direction for the spring force. That's right. But over here, I should get a negative spring force. Cool. If the block travels here and then goes backwards to this side and x becomes negative, that negative sign means this force is positive, which is the correct sign for that guy. So what I would say is this minus kx is correct for both of these free body diagrams. On this side, it pulls this way. On this side, it pushes that way. But that works for both of them. That's actually why I picked the equilibrium to be 0. That's always kind of a good practice to do. Cool. That's the only force acting in the x direction. I can now write max. Great. So there's my Newton's second law. That's the thing which I want to solve and get that. Okay, it's not set up to do that at all. There's an x. Clearly what I want to do is solve for x, but like the acceleration is different as it bounces around back and forth. The acceleration of the thing is different because the force is different, because the force is kx. So clearly I'm not really in a position to solve this thing yet. One thing we can do here is we can remember back to our calculus knowledge and what we did in physics 1, and note that we can write the acceleration as, in the x direction, the derivative of the velocity in the x direction with respect to time. And we can write the velocity in the x direction as the derivative of x with respect to time, which means the acceleration is the second derivative of the position as a function of time. So I can write that is d2x dt squared. Of course, it's not really a square, it's just a notation thing. So the acceleration is the second derivative of the position. Okay, so that's looks complicated, but it's good because it's got an x in it, right? And we want to solve for x. So let's try to put that into there and make some progress. So minus kx is equal to m now d squared x over dt squared. Cool. X's, I have a spring constant, I have an m, I have time. In principle, I feel like this is something I can solve because it's in terms of x, and that's what I'm trying to get to. But if I think a little bit more carefully, I look at this and I say, actually, I have no idea how to solve that. What I need to do is find an x such that if I do k times x, I get, on the other hand, I get something that's equal to m times the second derivative of that x. Like, how am I going to solve this thing such that when I take a second derivative, I get the same thing as the original times k? Like, it's confusing, right? That's because this is a differential equation. So this is something which we have an entire class here at Merrimack to study called differential equations. Most of you will take it after Calc 3, but we are not in a position to solve that yet. Okay, so that's a problem. We can't quite get there, but we can do something almost as good, which is we can prove that a solution to this, if I give you a solution, it actually is a solution to that equation. So what I'm going to claim is that this, which we are trying to show actually describes this set of motions, actually does solve this equation. So if I'm going to prove that this thing actually does solve this equation, what do I have to do? I got to plug x in for there, plug x in right there, and show the equal sign is true. So if I can do minus k times that, and then m times the second derivative of that, if they're equal to each other, then yes, this is a solution to that problem. So that's what I'm going to do, and that's what we're going to use as a proof instead of having to solve the differential equation to prove that this thing actually is a solution to this differential equation. Okay, so let's do that next. Okay, so the left-hand side of this is going to be easy because I just do minus k times this thing. So let's worry about that later. Let's worry about the right-hand side because the right-hand side is m dx squared dt squared. We need to take two derivatives of this to get that. So let's do that first. So let's now first take dx dt of this function. Now, this is going to be pretty easy. A is a constant, omega is a constant, phi is a constant. T is the only variable. So we already know that the A is going to pull out, so we're going to get an A there already. So what we want to do is we want to take a derivative of the cosine function. That gives you a minus sine function. And then, so let's do a minus sine. And when you do that, everything inside the sine function stays the same. But then you have to take the derivative of what's inside the sine function. That's called the chain rule, right? So, sorry, I should do a little parentheses here to make sure that I'm being careful about that. So the derivative of the cosine is the sine, minus sine. But now I have to take the derivative of the inside part here, omega t plus phi. Omega is a constant, phi is a constant. So the only thing that is a variable is t. So when I hit this thing with ddt, I only pick out a phi, right? I only pick out an omega. Because as I take this derivative, that thing's a constant, it goes to 0. This omega times t goes from 1 to 0, and I just get an omega. So the answer to the derivative is a minus omega times a sine omega t plus phi. Not so bad. Now we're going to do that again, because we need to get not to the first derivative, but to the second derivative. So take another derivative of this thing, d squared x dt squared. I'm going to do the same thing. Omega and a, they're constants, so they're going to get pulled out. In fact, I'll just do that. I'll just write minus omega a. Now I want to take the derivative of the sine function. Remember, the derivative of the sine function is the positive cosine function. It's only the opposite way, where you get the negative sign when you take the derivative of cosine. So this is going to be a cosine omega t plus phi. We've got to do the the chain rule again, which means we took the derivative of this, but now we have to take the derivative of the inside part. We did that already. We got an omega when we did omega t plus phi. So again, we're going to get an omega out of taking this derivative again, times omega. So let's write that again to combine all the things, just because we have another omega here. So this is now minus omega squared a times cosine omega t plus phi. Okay, so now we're in a good position to complete this process, because now we have the second derivative. It's right there. That's going to go right there. We have the x. That's right there. That's going to go right there. And so let's try to plug that stuff in. I'll try to color code this so it's obvious what I'm doing. Minus k, and I want to plug in the x from here. So that's going to be a cosine omega t plus phi equals, and then I have this m times the second derivative, so I'm going to do m, and then plug in the second derivative, which is right there, minus omega squared a cosine omega t plus phi. And so I put the equal sign in there because I'm like thinking they're going to be equal, but of course I kind of don't know if they're going to be equal. So I guess what I'm doing is I'm trying to demonstrate they are equal and what parameters there need to be here such that they are equal. But I can treat that like an equal sign. I can treat this like an equation and try to simplify it down and see if I get something which is a criteria which completes the fact that that is a solution of that. So let's try that. There's a cosine on either side. Cool. And actually, that's the whole trick, right? The second derivative of cosine is the same thing as itself, just with some minus signs and some constants. So that's how you actually solve these. You find things whose second derivative is themselves again. So trig functions are great examples of that. Anyway, cosine, cosine, cool. Bam, bam. A, cool. Bam, bam. Is that it? There's a negative sign I can kill. Bam, bam. I think that's it, but I've killed almost everything. And so now I get a really simple result, which is k is m omega squared. So what that means is that this omega was a parameter in my proposed solution. Now the proposed solution had an a in it too, but the a apparently didn't matter. So apparently all that matters is the omega. But if the omega satisfies this equation, then that is a solution to this. So that's cool. So as long as we pick our frequency such that it satisfies this, we have a solution. But even better, we can now solve this for the omega, which is very easy. Divide by m, take a square root. That's omega is the square root of k over m. Cool. And that's a fantastic result because now we know what the frequency of this oscillation is. It's the square root of the spring constant divided by the mass. So we've now basically solved everything there is to know about this physical problem with the exception of what A and phi is. So we still have to deal with what A and phi are. But if I give you a problem, here's a spring, here's a mass, it's bouncing back and forth. What is the angular frequency of the oscillation? There it is, right? You don't have to go through this whole calculus thing. You just say, oh, the angular frequency is the square root of k over m. Done. So there's our two key results from this first part of the class, is that we can solve these complicated differential equations by proposing a solution and then checking to see if the solution works. That checking process usually has some conditions associated with it, and as long as those conditions are satisfied, we can say, I know what the equation of motion is, it's that. Even better than that, the second thing we get out is we actually know something about the physics of the problem. Now, instead of not knowing how this thing moves, we now know what the oscillation frequency is if we just know what the spring constant is and what the mass is. Okay, great. So that's enough for this video. This really is a key component of how we study oscillations. It's motivated by the fact that we want to do Newton's second law in the oscillation situation, but we can't quite solve these differential equations yet. But if we propose these solutions, it works just as well as solving them. And we get these nice results which just say, oh, yeah, your guess is totally fine. It totally works as long as this parameter is satisfied. Okay, great. Thanks for watching this video. I hope this has been clear and getting you to a position of seeing the sort of character of the way we're going to use Newton's second law in this second half of the class to solve these sort of more complicated problems and apply them to oscillations and then eventually to electromagnetism. So great. Thanks very much, and I will see you in class.